where we want to test the difference between two means where we have dependent samples. So here we want to compare means by using a method that we call a paired sample technique. A paired sample may be appropriate when the members of the two populations have a natural pairing. Each pair in the paired sample consists of a member of one population and that member's corresponding member in the other population. I have no idea what that bullet point is supposed to mean, to be honest with you, so we'll have to edit this part out. In other words, the idea is you have a person that is in one population and you have the same person in another population, is basically what we have going on here. So let's just take a look at this example. I think this example will kind of bring a little bit of light into our thought processes here. So this is the example that I talked about the other day. So as an aid for improving student study habits, 9 students were randomly selected to attend a seminar on the importance of education in life. The table shows the number of hours each student studied per week before and after the seminar. So at alpha equals 0.1, did attending the seminar increase the number of hours the students studied each week? So here the idea is that we have a population that is the before, so I'll call this X1, and we have a population that is after, and here I will call this X2. So the idea is that if I have this before population and this after population, notice that each member, so each column of numbers here represents the same person in the before population and the after population. So that's kind of the idea that's going on. Notice that if you look at these, again, as two different populations, you have the same person in a before and an after. Pre-test, post-test. Left foot, right foot. Okay. So that's the important thing, is to notice between the other examples we were working on earlier, is that we had two independent populations where there was not a similar subject in both populations. Both populations were independent. They didn't have anything in common. So now I still want to continue working with this example and to kind of shed some light as to where we're going to be heading. So let's take a look at each one of these, and notice that we are asked if attending the seminar increases the number of hours that the student studied per week. So if we wanted to know if this intervention program worked with these students, all right, then what would we expect in comparison between the before and the afters? If we were to review all of these numbers here, if the intervention worked, what would we expect with these numbers, with these two different populations? We would expect increased study time in which population? In the after. So if the intervention worked, then we would expect these numbers to be larger than these numbers up top, right? What if the intervention didn't work? Then what would we expect with the numbers in both of these populations? They should be relatively close or the same. So when we want to compare two different numbers with the same subject here, how can I do this comparison? What have we been doing all semester long when it comes to do a comparison? Almost. There's one thing we have to do first. No, not the null hypothesis. Okay, let me. All right, let's go with the idea that the seminar did not work. So we just said that these numbers should be pretty close. How can I tell if these numbers are going to be pretty close? What could I do? Other way. Other way. Subtract them. Right? So if I want to know if the seminar did not work, then I would think that these two numbers would be fairly close to one another. And in fact, and if I want to determine if they are close to one another, then shouldn't I take their differences? All right, now let's still run with this premise that the seminar didn't work now. If these numbers are going to be close to one another, then what would I expect the differences to be close to? 0. All right, so let's take a look here. So here I have 0, -5, -3, -5, 1, -3, -5, -9, and 1. So again, working on the idea that if the seminar did not work, then I would expect these numbers to be close to 0. Or another way I could look at it is I could take these differences and then I could take the average of these differences, and what would I expect the average to be close to? 0. Now, if the seminar did work, and I took these differences just like I did, if I thought the seminar, now be careful, if I thought the seminar did work and I take these differences, then what would I expect a lot of these differences to look like? That is, what values would I expect these things to look like? I would expect to see a bunch of negative numbers down here, and the reason is because we said if the seminar worked, that means that the after population should be larger than the before population. Right? Or if I wanted to know if the seminar didn't work, then when I take these differences, then I would expect my differences to be positive. So there's not working, no difference, and then there was a difference. The seminar did work. We can look at it that way. So again, if the seminar did not work, then when I take these differences before minus the after, then I would expect these numbers here to be large, positive. Not large, but positive. If the seminar had no effect, then I would expect to see these differences to be close to 0. If the seminar did work, then I would expect these differences to be negative. Okay? We're going to keep that in mind here as we continue on. We're going to come back to this. All right, so suppose that X is a variable on each of the two populations whose members can be paired. Basically, the idea is that you have a dependency, so the dependency depends on if there's the subject is in both populations, if you will. The before and the after, pre, post, or whatever. You have another way of thinking of this is maybe the same subject on two different treatments. In other words, when we go back and look at the student intervention, there was the treatment where there wasn't an intervention, and then there's kind of a treatment where there is an intervention, and we want to see if it works. So we have the same person going through both treatments, if you will, and I'm using the word treatment very loosely, not like what we talked about in Chapter 1. So now what we'll do is for each pair, we will let D denote the difference between the values of the variable X on the members of the pair. So going back here, these guys right here, these are my differences down here. So we will call D the paired difference variable. It can be shown that the mean of the paired differences equals the difference between the two population means. That is, that the mean of the differences is going to equal to the mean of the first population minus the mean of the second population. So the idea is that if I could compute the mean for the before and compute the mean of the after, or if I knew the population means here and the population means here, and I take the difference, that should be very close, that if I compute the mean of the differences here, if I knew the distribution. Okay? Furthermore, if D is normally distributed, we can apply this equation and our knowledge of the studentized version of the sample mean. So again, the idea is that we have a small sample, we have the differences. If the differences are normally or approximately normal, then we know that when we go to talk about a test statistic, and we know that when we go to do all of that stuff, that our test statistic based on the data, based on the X bars, based on the standard deviation, should follow an approximate t distribution. This is everything that we've talked about since chapter 9, small sample case. Basically, this is saying the same thing on the differences, though. On the differences. Okay? So just to go one more step, suppose that X is a variable on each of the two populations whose members can be paired. Further, suppose that the paired difference variable D is normally distributed, then for paired samples of size n, the variable t, which is equal to d bar minus the mean of the differences, and I should subscript this with a sub-zero. Again, this is going to be under the null hypothesis divided by the standard deviation of the test statistic here, or of our sample statistic, d bar. So again, inverting and multiply for computational purposes, this is going to be our standard, our studentized t test statistic, where we have degrees of freedom is n minus 1. So this d bar is going to be the mean of the pairwise differences, and s sub d is going to be the standard deviation of the differences. So these d bar and s sub d, when we have the data, is going to be something that we're going to have to compute. So that forms our foundation. So step number 1 to perform a pairwise or a paired t-test, what we call a paired t-test, is we're going to state the null and the alternative hypothesis, and we're also along the way going to compute d bar and the standard deviations of the differences. We're going to compute our test statistic, which we've just discussed. And then we're going to sketch our t-distribution with the appropriate shaded region, that is upper, lower, or both tails, and compute our t-critical value based on degrees of freedom n minus 1. Step number 4, we'll make a decision based on what region our test statistic that we computed in step 2 falls in. And then finally, step number 5, we're going to summarize our results. So in other words, we're going to notice that the hypothesis test format is exactly the same that we've been talking about since chapter 9. So conceptually, everything is pretty much running the same. Alrighty, so you ready to work a few examples? Because that's about all the theory I'm going to go into based on this. So let's flip back here to our seminar. All right. Now remember, when we're doing these, when we're formulating our null and alternative hypothesis, I guess I should state up here, if you want to annotate this, when we state the null and the alternative, the null is always going to be in the form of mean of the differences is going to equal to something, and the alternative is going to be that the mean of the differences, and then it's going to be either greater than, less than, or not equal, depending. So in other words, when we state the null and the alternative hypothesis, and we're using a paired t-test procedure, we are going to state in terms of mu sub d. So coming back to this example here, step number 1 says to state the null and the alternative hypothesis. So again, following the exact same procedure that we've been following since chapter 9, notice here, did attending the seminar increase the number of hours the student studied per week? Is that going to be a null or an alternative hypothesis? The alternative. So I want to talk about mu sub d. So now if attending the seminar increased the number of hours, what do you think how we're going to state our null hypothesis in terms of the mean of the differences? 0, I'm sorry. You were correct. Sorry, Randy. You're right on the ball. It's me. I admit it. It's me. Because, again, as we stated, if the seminar did work, we would expect the after to be greater than the before. Therefore, the mean of the differences, so we would expect these numbers to be negative, to be less than 0. So under the null hypothesis, we would expect the mean of the differences to equal 0, saying that there's been no effect. So step 2 is to compute our test statistic. So t test statistic then is equal to, well, it's going to be d bar. Oh, we didn't compute the summary stats yet. Before we get to step 2, we got to compute the summary stats. So what I'd like for you to do is take your calculators out, put the before into L1, and put the after into L2. So stat edit. So 9. Oh, okay. It looks like I already have them there. Cool. So after you get those in, does everybody have them entered? Are we good? All right, so here's what we do to compute these differences down here. We can let our computational device do the work for us. So what we want to do is we want to take all the numbers in list 1 minus all the numbers in list 2, and then what we're going to do is store them into L3. So that's all we have to do. So we'll go second L1 minus second L2, and now we will push the store button, which is right here, store in second L3. So L1 minus L2 and store it into L3, press enter. So now all of our differences is in L1, or is in L3. So now we need to compute D bar and S sub D. So all we have to do is come back over here and just go stat calc, and we'll choose our single variable statistics. All right, but before we do anything, we have to tell it which one we want the mean and standard deviation. So that's going to be of the differences, which is located in L3. So we go second L3. So we have a mean of X, our D bar then is negative 3.11, and our standard deviation is 3.33. Is that what everybody came up with? All right. So we have negative 3.11 and 3.33. So again, when we do this, it's just going to be L1 minus L2 store into L3, and then it's going to be stat, single variable stat. So again, please refer to the calculator tutorial that I have out. Go back to the stuff in chapter 3.
Can you show me that screen that you had with the calculator on it? So I can make sure I can move.
It was right here. Negative 3.11 and 3.33. Yeah, right there. All right, so step number 2, that's okay because you can always go back and make sure you got your numbers typed in correctly. Right. Step number 2 is to compute the t-test statistic. So remember, the t-test statistic is going to be d bar minus mu sub d under the null hypothesis times the square root of n divided by the standard deviation of the differences. So d bar is negative 3.11 minus, well, mu under the mean of the differences under the null hypothesis is going to be what? 0. And again, this is one of those 99.9% of the times this is going to be the case. So that's 0, so now we can just go times the square root of 9 divided by 3.33. So if you compute this, you should come up with a test statistic of negative 2.80. So step number 3 is to sketch our region. So we're going to draw a T curve. And we got a lower bound test, so I'm going to shade this lower region here. And our alpha level is 0.1. So now we need to come up with a T critical value. So again, you can go to the chart or your calculator, however you want to compute this. So the area is going to be 0.1, and our degrees of freedom is equal to 8. N minus 1 is 8. So 9 minus 1 is 8. So going and looking up the critical value on the T chart or using your calculator, I came up with negative 1.397. So you can either go to the tables, look up the column of 0.1 and go down to 8 degrees of freedom, or use the inverse T, 0.1 comma 8, and you'll get this number. So now we have to make a decision, step number 4, so negative 2.80. So our test statistic looks like it falls way over here. So is our test statistic in the rejection region or the non-rejection region? Rejection region. So we can reject the null hypothesis. So we can come back, and what's the short run conclusion? Did the intervention work or did the intervention not work? It worked. So we can formally come back and say at alpha equals 0.1, the data indicates that the attending the seminar increased the number of hours that students studied per week on average or something like that. All right. So again, can you see how this is a paired, that is that you have a subject that is participating, if you will think of the before and the after as two different populations. Can you see how each subject then is part of each population? So again, when it comes to working with two populations, the first thing you've got to ask yourself is this an independent paradigm, or am I going to use a paired t-test? And you'll know that because you have a subject that is under, or that participates in both populations. Whereas in the independent, you have two separate populations and the subject does not participate in both the populations. So a dietitian wishes to see if a person's cholesterol level will change if the diet is supplemented by a certain mineral. 6 subjects were pre-tested, and then they took the mineral supplement for a 6-week period. The results are shown in the table. Can it be concluded that the cholesterol level has been changed at alpha equals 0.1? All right, so the first thing that we have to ask ourselves is that question number 1, do we have one population or 2 populations? Survey says 2 populations. Then when you ask yourself, and you have the 2 populations, then you have to ask yourself, are the 2 populations independent or are they dependent? Yes, what? So we have the subject that is actually in both populations, right? So that means we conclude then that we're going to do a paired t-test. Yeah? Let that sink in for a minute, or has it sunk in? So step 1 is to state the null and the alternative hypothesis. So again, when we state the null and the alternative, it has to be in terms of the differences. So let's come over here, and again, can it be concluded that the cholesterol level has been changed? Is this going to be the null hypothesis or the alternative hypothesis? The alternative. And here we're just asking if it's been changed. So that means that the mean of the differences does not equal 0. And the null hypothesis then is that it does equal 0. That is, that this thing did not change my cholesterol level. So continuing with step 1, we need to compute D bar and S sub D. So why don't you enter, again, notice how these are labeled X1 and X2. So let's put the before into L1 and the after into L2. And again, we'll just go L1 minus L2 and store that in L3. So for D bar, I came up with 16.67, and S sub D is 25.39. Do we concur? All right, so step 2 is to compute our t-test statistics. So t equals, so it's going to be D bar 16.67 minus mu under the null hypothesis, which is 0, times the square root of n, so we can go root 6, divided by the standard deviation of the differences, 25.39. So I came up with 1.161. 1.61. I think I said 1.161. So step 3, so we need to draw our t distribution, and we have a two-tailed test. So how much area is going to be in each tail? 0.05 is in each tail. And what is our degrees of freedom? 5. So again, however you want to compute these, either using the chart or the inverse t, you should come up with negative 2.015 and 2.015. So step 4, we have to make a decision. So our test statistic is 1.161, which is probably about right there. So does our test statistic fall in the rejection region or the non-rejection region? Non-rejection region. So we're failing to reject the null hypothesis. So what is the short run answer? Did this mineral supplement reduce the cholesterol level or not? No. So at alpha equals 0.1, the data indicates that the average cholesterol level did not change with this supplement. Okay. Want to try one more? So glaucoma is the leading cause of blindness in the United States. Ehlers measured the corneal thickness of 8 patients who had glaucoma in one eye, but not the other. The result of the study was published as the paper, The following are the data on the corneal thickness in microns. At the 10% significant level, do the data provide sufficient evidence to conclude that the mean corneal thickness is greater in normal eyes than in eyes with glaucoma? So again, we need to state the null and the alternative hypothesis. So we can come back here. Do the data provide sufficient evidence to conclude that the mean corneal thickness is greater in normal eyes than with glaucoma? So we need to state this in terms of mu sub d. So again, we're going to take the normal minus the glaucoma. So what do we want to write for our differences up here? It's greater than 0? Because we're going to take normal minus glaucoma, and we want to know if the normal corneal thickness is greater on average than the glaucoma. So the differences then should be positive. So the null hypothesis says that the mean of the differences is equal to 0. So now we need to compute d bar and S sub d. So why don't you guys take a few minutes, plug the data in, and compute d bar and S sub d, and then continue on with the rest and finish it off. And I'll come back in a minute, and then I'll put my solutions up. Okay, so for d bar, what'd you guys come up with? 4? That's what I came up with too. And for S sub d, 10.74. So the t-test statistic for step 2. So t equals d bar So 4 times the square root of 8 divided by 10.74. So what do we get for our t-test statistic? 1.05? Okay. And now we have to draw our t-distribution. So that's pretty darn close. So this is an upper-tailed. So the area here is 0.1. So the degrees of freedom is 7. So survey says that the t critical value, everybody, what'd you come up with? $1.415. So now we have to make a decision. So our test statistic 1.05 falls right here. So do we reject or fail to reject the null hypothesis? Fail to reject. So what's the bottom line? Is there a difference between the corneal thickness for normal eye and a glaucoma eye or not? No. There's not.